Okay, welcome AP Chemistry students. This is a video podcast on Chapter 17 in your textbook, which is getting us back into the idea of thermodynamics. This is entropy and Gibbs free energy. So just to kind of give you a reminder, entropy is symbolized as a change in delta S, and Gibbs free energy is the change in delta G. So if you remember that from your first year course, that's awesome. Otherwise, it's part of what we are going to talk about in this chapter, along with, of course, other material expanding on what you learned in your first year course. Thermodynamics is a process where you're looking at the energy relationship, and now we will also be looking at the disorder relationship of a chemical reaction. You should know that term spontaneous, which I have right here. What a spontaneous reaction means is that it will happen on its own without outside intervention. Thermodynamics let us predict whether a process will occur, but it doesn't give us any amount of time that it will happen. So if we're looking at this graph here, and what thermodynamics basically tells us is where the reactants are starting, where the products are starting. It doesn't really tell us the pathway that it gets to or how it gets there. That is under the domain of kinetics. But thermodynamics starts out where the beginning energy is and where that final energy is. And of course, when we think of thermodynamics, we're thinking of delta H, which is entropy or enthalpy. Okay, which you guys know is energy at a constant pressure. Okay, so reactions will happen spontaneous, and one notice about a spontaneous reaction is that AP has changed their wording on it, and they are using the word thermodynamically favorable. That's a big word. So what is thermodynamically favored? Is the reaction thermodynamically favored? If that's an F, by the way. If the reaction is thermodynamically favored, it means the reaction is spontaneous. It will proceed on its own merit. If it's not thermodynamically favored, it is non-spontaneous, and it will not proceed on its own. And the picture that I have here is one that you may be familiar with, and that is a spontaneous reaction when rusting occurs, when it becomes in contact with the water. So it's an inevitable reaction that this iron is going to become an iron oxide. So that is a thermodynamically favored reaction. So entropy would be one thing we want to talk about here first. There's actually going to be two driving forces that govern a reaction. So the two driving forces are enthalpy and entropy. Enthalpy is that delta H that you've studied before. We studied in the earlier chapter last term. Entropy, which is symbolized as S, is a driving force for a spontaneous reaction, and it is a measure of disorder, or the amount of randomness that can occur in a chemical reaction. You should read through your textbook, especially this first few sections in chapter 17.1. They have a couple of case studies that talks about randomness disorder in terms of positional probabilities. And if they want you to think about, if you have a container such as this right here, a bulb that contains some gas, and you have it closed off, and you have another bulb that's attached with a vacuum in it, if you open this up, the gas molecules are going to move to that evacuated chamber. You've increased the positional entropy in this situation. So entropy is a measure of randomness or a measure of disorder. And when we look at it in terms of chemistry, we look at, as I said, positional entropy. And we think about gases as having a lot more entropy than your solids do. Liquids would be in the middle, but very closer to solids than gases. Gases have a tremendous amount of entropy. So when we take a look at thermodynamics, there are also laws that govern thermodynamics. And actually, we're going to talk about the first law of thermodynamics, and that is that energy is conserved. Okay, so energy is constant. It can go in different forms. You can go from chemical to mechanical. You can go from mechanical to electrical, and so on and so forth. You can go from potential energy to kinetic energy, but the energy is constant in the universe. The second law of thermodynamics says that in a spontaneous process, there is always an increase in the entropy of the universe. Or in other words, the universe is in a state of increasing entropy. Second law of thermodynamics. In chemistry, what that means is that we can use a chemical equation to predict if the entropy is increasing or decreasing. So entropy, which is disorder, is the change in delta S. And if you look at solid calcium carbonate decomposing into solid calcium sulfide and CO2, this would be an increase in a change in entropy from calcium carbonate to these two products. So we would say that the sign of delta S is positive. The second reaction that we have here, sulfur dioxide plus oxygen gas going to sulfur trioxide gas, would be a decrease in entropy. So the change in entropy would be negative. So we can use the chemical equation to determine the change in entropy. You should also make sure that you're reading through the textbook on the theories of the positional entropy relating to chemical equations. That would also be very helpful. All right, so in our first year course, we also talked about Gibbs free energy. And Gibbs free energy would be what we basically call the tiebreaker. So it breaks the tie between the enthalpy and the entropy. Now, one thing that we'd have to remember is that delta H, which means enthalpy, means that nature prefers exothermic reactions, which have a sign of negative. Second law of thermodynamics says that the change in entropy is increasing, or basically the universe is increasing its entropy, so that has a sign of positive. Now, if these two driving forces are in the right thermodynamically favored states, where delta H likes to be negative and delta S likes to be positive, it is a no-brainer. The reaction's going to happen spontaneously. But what happens if one of these two states is not the way nature likes? For instance, we know that endothermic reactions can occur. So an endothermic reaction has a positive delta H, which is not what nature prefers. What would matter is the temperature, and the amount of delta S would have to be significant enough to compensate for that positive delta H. So a process at a constant temperature and pressure, which is spontaneous in the direction in which Gibbs free energy decreases. So what that means is that delta G being negative means that the reaction is going to be spontaneous or thermodynamically favored. If that delta G is positive, then it is non-spontaneous or thermodynamically unfavorable. This is a chart that you should memorize. I have seen it many times on the AP exam, and maybe memorize isn't really the correct word. What I would highly recommend is that you understand the position of the delta H and the delta S based on Gibbs free energy. And when delta G is negative, that's what we need in order to have a spontaneous reaction. We can look at our delta H and our delta S, where, do you remember that this stands for temperature? And the temperature has to be in Kelvin. Oh, also, the other thing that I would tell you to caution you on is make sure that you are looking at your units. Typically, delta H is in kilojoules and delta S is in joules. So that would be another thing that I would caution you. But now, if we're going to take a look at a reaction in which delta H prefers to be negative and delta S prefers to be positive, that's a no-brainer. The reaction is going to happen spontaneously, thermodynamically favored, because these are the two states that nature likes. And what if it is an endothermic reaction and you are losing your randomness, or you're becoming more organized? This reaction is not spontaneous at any temperature. Doesn't mean that the reaction can't happen. We would just have to put an outside force onto this reaction in order to make it happen. But what's interesting is what happens if you have one state in which nature does not approve, but the other state nature does approve. Then you're looking at delta G here to determine if it is going to actually indeed produce a negative value. So here where it says spontaneous at all high temperatures, if this is positive, this temperature has to be large enough that this negative piece will overcome the delta H. And the same goes true with this. If it's negative the way nature likes it, but it is negative for the entropy the way nature disapproves, then a negative times a negative makes a positive. We do not want this term to be very big, that it will overcompensate the negativeness of the delta H. So those would be very good things to make sure that you understand. So what I'm going to ask you guys to do now is to just pause this video, and I want you to read these and determine if it's going to be spontaneous, not spontaneous, or cannot tell and explain. So pause the video, go through this now. Okay, welcome back. And I took a look at this slide as well, and I put some markings on there in terms of exothermic and for the delta H, and what the mark was for the delta S, which is positionally random, is how they were naming that. And when I say it depends upon the temperature. So make sure that you guys also got the same answer, and you can explain how temperature will affect your answers. That is it for this video. I wish you good luck and see you next time.